So, with the help of this relationship we can say that tau is having relationship with r. So, tau is related to r, and this constant we can find out when r is equal to 0, then shear stress is 0, and when r is equal to capital R, then tau is maximum and it will be known as, it is designated as tau W, wall shear stress, right. So, in this manner we can say that shear stress varies linearly. This is for real fluid. If we have a ideal fluid or inviscid fluid, in that case viscosity is 0, mu is equal to 0, and even if we have a flow through a pipe, this will be the profile, where everywhere we have a constant velocity, right. So, with the help of this equation we can find out del P, where del P is equal to 4L tau W divided by capital D. Now, if we have laminar flow, in that case shear stress may be written as minus mu du over dr, because we know that in very first chapter we have studied shear stress is equal to mu du over dy. Shear stress is equal to viscosity constant multiplied by velocity gradient in y direction, du over dy. Now, this equation, since here we are using r, and what is y here? Y is the distance measured from solid surface, from solid boundary, right. And what is the solid boundary here? This surface is solid boundary, this surface is solid boundary, and here we are going to develop relationship in terms of radius, and radius is being measured from the this line, right. R is equal to 0 and R is equal to capital R. So, what is the relationship at this point for du over dy? Tau is equal to mu du over dy, and what is y here? Y is the distance measured from solid boundary, this distance. So, this y is equal to capital R minus small r. So, y is equal to capital R minus small r. So, dy is equal to what? Dy is equal to minus dr. So, if we substitute this dy is equal to minus dr in this equation, our equation reduces to tau is equal to minus mu du over dr, right. So, substitute this tau W is equal to minus mu du over dr, and substitute this tau W in the previous equation. Del P over L is equal to 2 tau divided by R. So, in this case du over dr is equal to minus del P divided by 2 mu L R. Now, if we integrate this equation by bringing this dr here, integrate du minus del P, at a particular section this del P is constant, mu is constant, L is constant, only R dr, these are variables. So, R dr is inside the integral sign. If we integrate this u minus this del P divided by 4 mu L, which remains same, this is R square plus constant of integration C1. So, how do we get this constant? This is done with the help of boundary conditions. What are the boundary conditions? To have no slip when R is equal to capital D by 2, means at the surface, inner surface of the pipe, the velocity is 0. So, this constant can be calculated with the help of one boundary condition. So, this constant is equal to, when u is equal to r is equal to d over 2, u is equal to 0. So, substitute here this boundary condition and we will get C1 is equal to del P divided by 16 mu L d square. Substitute this C1 in this equation for calculating the velocity profile. What is u here? U is a velocity at a particular section which is function of radius. So, ur is equal to del P d square divided by 16 mu L 1 minus 2r divided by d square. This is equal to, if this whole thing del P d square divided by 16 mu L is written as Vc, then this may be written as Vc 1 minus 2r divided by d whole square. Right. So, with the help of this we can say that u is having parabolic relationship with r. Right. So, here we can write this equation in terms of the tau w also by invoking the equations which we have discussed for the wall shear stress. We can write the shear stress in this form also. ur is equal to tau w d divided by 4 mu 1 minus r divided by capital R square. Now, this equation gives us the velocity profile. So, with the help of this equation we can plot the velocity profile, and this will be parabolic in nature and it can vary only in this manner because d over dr is less than 0. So, it means that it will decrease from the center line. So, this is the laminar velocity profile at a given section, and Vc is known as a maximum velocity here or center line velocity here. So, with the help of this equation we can find out that how does velocity vary at a section. So, it varies in a parabolic nature, and at a center line this velocity is maximum, and at the wall velocity is retarded to 0 to satisfy no slip condition.